Hi, welcome back to es346 Basic Thermodynamics. This is Module 3.5, Compressibility Factor. The section in the textbook is Section 3.7. Here are the two learning outcomes from this module. At the end of this module, you'll be able to evaluate the degree of idealness of a gas, and you'll be able to use the compressibility chart to find non-ideal gas properties. So let's go back and talk about the ideal gas equation that we did in the last module. On the left here, again, I have plotted temperature as a function of specific volume. And this is showing the air in the ideal gas equation. The ideal gas equation is PV equals RT. And so often we have very low air if we have low pressures and high temperatures. However, if we don't have a low pressure and a high temperature, but we don't have access to a chart, we'd like another tool. And that's the tool that we're going to use, which is another equation of state, or often written as EOS. The ideal gas equation is an equation of state, and today we're going to look at another equation of state. The equation of state is the compressibility factor, and I've written the definition of it here. Capital Z equals PV over RT. I could rewrite this equation and say that PV is equal to Z RT, and we see it's very similar to the ideal gas equation, except we have this new parameter, capital Z. Now, if Z, capital Z, was equal to 1, we would have the ideal gas equation. So when Z is equal to 1, it's an ideal gas. Now, if Z is some value other than 1, the behavior deviates from the ideal gas equation. And so that's what Z does. Now, Z is not a constant. Z depends on the pressure and the temperature. So at different temperatures and pressures, Z takes a different value. Now, recall, at low pressures and high temperatures, we can use the ideal gas equation. Under those conditions, Z approaches 1. Let's look at Z a little bit more. So here I'm showing what's called the compressibility chart. This is the Niels-Olber compressibility chart, named after the two people that came up with this idea. What is plotted on the left is capital Z, which I'll remind you, Z is equal to PV over RT. And what is plotted on the x-axis down here is reduced pressure, P sub R. And P sub R, I've written the definition up here, is the pressure normalized by P critical. Recall, P critical is the point at the very top of the mountain on the phase diagrams. Now, each one of these lines, these green lines on here, corresponds to different values of T sub R, which is the reduced temperature, which is the temperature normalized by the critical temperature. And so each one of these lines corresponds to a different value of T sub R. Here's T sub R of 1.5. Here's T sub R of 1.3. What is also shown in all these different icons are different gases. And as you see, they all tend to cluster along these lines, which means that Z does a good job of representing their behavior in the non-ideal region. Now see, when I say non-ideal, here we look at the value of Z. Ideal gas is when Z is near 1, so that would be up in this upper region up here. That would be where the ideal gas law works well. There's a large region down here where we have temperatures that not as high and larger pressures. If I'm at a very low pressure up in this region, Z is near 1, higher pressures it's not. So then if I'm in those conditions when I can't use the ideal gas equation, I'll use this compressibility chart to find a value of Z and use that to find my property values. So let's go ahead and do an example. The question says, what is the specific volume of CO2 at 150 degrees Fahrenheit and 200 psia? So I'm asked to find the value of little v. I'm given a pressure and I'm given a temperature. I'm going to use the compressibility charts. So I've got PV is equal to ZRT. I'm given P, I'm given T. I need to find my value of Z in order to calculate for R. So in order to do that, I need to find out where I occur on this table. So let's go ahead and calculate our reduced pressure. Now, reduced pressure is the absolute pressure, T1000, over the critical pressure. I find that on table A1. This will be A1E. We're in English units on this one, and that is 1071. So my reduced pressure is about 1.85. So looking on the chart, I'm right around there. Now I also need to calculate my reduced temperature, and I'm at a temperature of 150, and I need to convert that into absolute. So that's 150 plus 460 divided by the critical temperature. I get that again from table A1E. That is 547 degrees Rankine. And I have a reduced temperature of about 1.1. So now I'm going to come to the chart. I'm at, on the x-axis, of PR value of 1.8. I go up to the line, which I've got there, of TR of 1.1, and I realize that Z is equal to about 0.4. So now I can plug that into my ideal gas equation and find my value of V. Let's do another example that's not quite as straightforward as the other one. Now I'm asked to find the pressure. I'm given a temperature and I'm given a specific volume. So what's different now is I have specific volume instead of pressure. So if you look closely at this diagram, you'll see these dashed lines that are going from the lower left to the upper right. And those are values of V sub R. Now V sub R is defined differently than reduced pressure and temperature, and it's given down here in the diagram. It's pretty small to read, but V sub R is the volume times P critical over RT critical. So I can determine what my value of VR is in this problem. I have 0.037. My critical pressure of 1071. The value of R in this problem, 0.244. We're working with carbon dioxide. And my critical temperature is 547. And that will give me a reduced volume of about 0.3. So that means that if I look on the dashed lines, this one right here is my 0.3 line. And the other thing to remember is TR previously was equal to 1.1. So here we go. We've got a reduced volume of 0.3, a reduced temperature of 1.1, and I'm going to look at where those intersect on this diagram. And it looks like it's about right there. So then I've got a value of Z, or actually I can read, I don't even need to read Z, I can read straight down to find my reduced pressure. PR is equal to 1.6, and I can use that to calculate my actual pressure. So P is equal to P reduced times P critical, 1.6 times 1071, and that will give me a pressure of about 1714 psia.